Welcome back into Module 2, and this is Part 5, the final part, which is all on star formation and light. So in previous videos, we have talked, of course, about energy and the energy that was created from the Big Bang. We've looked at the timeline behind the Big Bang and the cosmic microwave background, giving us 13 billion year old evidence of this event occurring. We've also looked at how the shifts in light signatures of stars gives us information to star locations, but also the continual expansion of the universe. But we haven't looked at how these stars are producing their own light. And to answer that, we must first consider the basics behind what is a star and how do they function. Right? So first, a bit of mind-blowing research around stars. This image from NASA shows us a cut of our own Milky Way galaxy. Right? So just this Milky Way here. This is just a little cut blown out to here. Right? So the amount of stars estimated to be a part of the Milky Way, the number is extremely hard to pinpoint, but scientists have made approximate guesses of anywhere from 100 billion to 400 billion stars. That's just in our Milky Way alone. I mean, look at the amount just in this little snippet, right? So that's not counting the other countless stars in the other 100 to 200 billion potential galaxies in our universe. So that's insane. All right, so that is the large scale of stars. Okay, but what's the small scale of stars, and where do we start our look at star formation? Well, with our own star, of course, the sun. What an amazingly beautiful and powerful object. And what is the craziest is that we think of this as, this bright circle in the sky, and this smaller circle that we look up to. But when you compare it to the actual size with that of all the planets, including our own, well, we are actually very, 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 very small. Pretty amazing. But so look here, this is Earth, right? You got Jupiter and Saturn, and there's your sun. So how are these made? How was our sun made? How does it work? Well, the majority of stars form from clouds of gases that are swirling within galaxies, and these are sometimes referred to as solar nebulas. Now, these clouds, they collect to the point where they have a large amount of gravity, and this causes all of this matter to begin collapsing inward on itself. So then, as the condensing matter begins to heat up from all this pressure, right, the core begins glowing, and this forms what is known as a protostar, or an early star. But according to Kiel University, once this protostar continues to heat up to around 15 million degrees Celsius or so, it is hot enough to begin nuclear fusion in its core. And at that point, it can officially be called a main sequence star. Now, nuclear fusion continues in the core, and this allows more and more energy to be released. And this energy release is what allows the star to, quote, shine, as we call it. So, how does this happen? What is nuclear fusion? Well, the sun is made up of all these different atoms. Right? Remember, all of these atoms came from those original clouds of gas, that of course were originally formed during the Big Bang. But these clouds of gas collected to form that star, right? So there's all these atoms. The atoms are mainly hydrogen, approximately 94%, with approximately 6% helium atoms. Right? Now, what happens is that the core is so intensely hot, and there's so much gravitational force, that the normal forces that exist between protons that typically cause them to repel each other, bounce away from each other, these forces can be overcome. And this turns the star's core into a giant melting pot of superheated protons. So this then allows these protons to actually fuse together. They become almost glued together. And as this is happening, some of these protons are transmuted, which means they're basically changed into a neutron. So now when you have the proton-neutron combo, like you see over here, this is called deuterium. That's basically an isotope of a hydrogen atom. At each stage of this process, every time you have a fusion of particles, okay, this is the energy here that we need to know about. Every time you have a fusion of these particles, energy is released as gamma rays, or we can also call them photons. And photons are exactly what we are seeing as the sun's light. They travel all the way through the vacuum of space, transmitted to our world, to our eyes, making the sun our ultimate energy source. So photons are basically the fundamental particle of light. They have a unique property, though, in that they are both a particle and a wave. Right? So this is what allows photons unique properties like refraction and diffusion. So they're very unique particles. However, they're not quite the same as other elementary particles. You see, they have interesting characteristics that are not usually commonly observed. One of which is that physicists theorize that photons have no mass, and they also don't carry a charge. So nonetheless, interesting particles that drive our world as we know it, all thanks to nuclear fusion in the core of our star. So what's great about understanding the light released from stars is that scientists can use this information. They can put it together with the information we just learned about how the wavelengths of light behave depending on their movement and direction, and scientists can determine if a star is moving towards us or away from us, all based on the light and photons released from it. Scientists can also take all of this information about the amount of light given off, otherwise the luminosity or electromagnetic power, or also we could call it the brightness of the stars, right? They can take all this with other data and research to make determinations about the size of stars, the composition of stars, and the age of stars, which helps inform us about how long ago stars began to form. And we can see this whole size comparison with the sun being invisible. It's so small, it's just a speck over here, compared to some of the largest identified stars in our galaxy. Pretty amazing stuff. All right, so nuclear fusion, right? We had the proton transmuted into a neutron. You have the energy release of these photons, right, being released. So the release of photons from the fusion in this first step with deuterium being formed is not the only part to fusion. You see, those atoms then continue to fuse together. More protons fuse to that, creating helium-3, and that releases more photons. Now, step 3 of fusion, those helium-3 atoms will collide, and that fuses to form a helium-4 atom. That's the naturally occurring helium in our world. And you see here, though, there was some extra protons. Well, these excess protons are released, and they go off, and guess what they do? Well, they begin colliding and fusing together, and they begin the fusion of even more particles, while again, more and more photons are being released as energy from the star. So nuclear fusion is constantly occurring in the core of a star. And as stars mature, fusion begins to create heavier and heavier elements beyond the mass of hydrogen and helium. So now carbon can be formed, and oxygen, and neon, magnesium, all the way up to heavy metals like iron. So our sun has small percentages of each of these elements. So we can now start to understand that stars are kind of like the factories of the universe. They're fusing heavy elements together, making new elements. And then, upon the death of a star, which occurs when certain star sizes begin to make iron, well, this iron is too heavy, it's too dense, and the star begins to collapse on itself. And that creates the explosion we know of in certain size stars. It's called a supernova. And this then releases all of these new elements into the space around it. Well, guess what happens to all those elements that are blasting out from this star death? Well, they, of course, collect again, and over time they form new stars with even new elements at the core. Other structures then begin to form from all these elements, like planets like the one we live on. So all of the elements found on Earth were out in the universe at some point, and we have been fortunate enough to have the perfect combination of all of these to form the spinning, life-giving sphere that we call home. So once again, we have a lot of information that has just been thrown your way. So quick review. What do we know? Well, there are a ton of stars out there. And by ton, I mean hundreds of billions, maybe even trillions. We don't even know at this point. All right, these stars can be a range of sizes. Our sun is a pretty big one, but there are some that are as big as the orbit of Jupiter. So there are some really, really huge ones out there. Once stars hit a certain size, gravitational force, and temperature, nuclear fusion can begin, and fusion is all about taking this superheated soup of protons and neutrons and fusing them together to form new elements, and of course in this process, photons are released, which is what we know of as the heat and light from the sun. And remember, nuclear fusion also makes heavier elements, which are one day released into the universe and then recombined to form new structures, like new stars, asteroids, comets, and of course, planets like our Earth. Now, again, there was a lot of stuff in this video, so make sure to watch it back if you have questions. Check out all the great resources that were used to put this together. And if you're interested in this stuff, like I've said always before, do your research, read articles, check out images. There's some amazing stuff out there waiting for you. I'll see you in the next module.